All right, static fans, this is video number 4. It's all about the electric field strength. So we already talked about forces. We did the hard math stuff already. If you can do the force stuff, you can do the field stuff. Okay? So the math doesn't get any harder. They're both vectors. Force is a vector. Fields are vectors. So it's the same kind of math. It's not anything brand new. So, but there is a difference between force and fields. Okay? So this field idea is a way to visualize what fields are like. You don't have to have a second charge. For example, there's a force between the Earth and another mass because this mass is in the field of the Earth, or the Earth is in the field of the ball, however you want to think about that. But we normally, since the Earth is so much more massive than the ball, we think of the field from the Earth because the field from the mass of the ball is not going to be all that great. But there is a certain field which we talk about in terms of G. Well, the same thing between two charges here. We tend to have one large charge and it has a field around it, like the Earth has a gravitational field that's very measurable. The field of this mass, not so measurable. We do the same thing with little charges. This charge is so small that there's not much of a field to it, at least it's kind of hard to measure. However, it's much more easily measured is a larger field like this. So you can use that kind of as an analogy to talk about how they're similar to each other, at least in terms of fields. Okay, so the way you measure the G field in your AP1 is by your force per mass. You basically put some kind of a mass on a spring scale or some kind of force measuring tool, and you measure the force or the pull of gravity on it per the mass. Bam, there you go. And if you did this at the surface of the Earth, you found that was 9.8. If you would hang a 1 kilogram mass on your spring scale, it would be a force of 9.8. Hence, the field at the surface of the Earth is 9.8. You could go to a different part of the Earth with that same 1 kilogram mass, and you find, bang, that 1 kilogram mass still weighs 9.8 newtons. You go twice as far away from the center of the Earth, the two Earth radii. Well, that's 1/4 the gravitational field. That same 1 kilogram would be 1/4 of the 9.8, hence it's 1/4 the field. Well, we're going to do the same thing electrically. So that little spring scale with the mass hanging on it is a way to measure what the gravitational field is like. Now we're going to use that same idea to measure what the electric field is like, not with a mass, but with a known test charge. The key is you got to know what that test charge is. Just like in measuring that field, you got to know what that little mass is over here. You have to. Otherwise, you just have a force per what? You don't know. Alrighty, so here we go, guys. So the G is the force of gravity per the mass. Electric field, same idea. The electric field is the electric force per the amount of charge or the test charge over here. See, the reason we use a really small test charges, and if we could use a big planet over here for a mass, we could find the force between the two. But then you got the fields interfering with each other. So by having a very small mass, the field is almost imperceptible in a small mass, and the same is almost true for this test charge. The point is, we don't want that test charge, the field of the test charge, to mess with the field of this larger charge over here. So you make it a really small one. Okay? And to measure that field, you measure how much force is applied to this test charge of a known amount. And that force per charge would be a measurement of the field. Just like your force per mass is a measurement of the gravitational field, your force per charge, because remember, mass doesn't have anything to do with electric charge or electric forces. Charge has everything to do with electric forces. So all you have to do is measure how much force you have acting on a known charge is the key. That's how you measure what a field, what the electric fields are. Okay, so charge is small, just like that mass is small that you have on your spring scale. It doesn't have to be positive; it can be negative. But so everybody in the world does things the same. We all say it's going to be a positive. With gravity, it doesn't matter because there's no repulsive gravitational force. It's all attractive. There's not a positive and negative mass. There is a positive and negative charge. For that reason, we've all determined on this planet that we're going to say this is a positive test charge, so we get the direction of the field correct. Okay? So the direction of the the gravitational field is towards the Earth, okay, just in this direction. But it can actually be away from a charge, depending on what this charge is over here. So that's why it has to be a positive charge, because we're very positive people on this planet. We don't like to be negative. So that's what we say is standard. There's a very small positive test charge here, and that field will be measured by the measured force per that known test charge. Okay, it is a vector quantity, it is in a direction. So fields point towards negative charge, just like fields point towards the Earth gravitationally. Fields point towards negative charges, but away from positive. So what happens is there's an attractive force between the two, and this is pointing towards the negative because that field is pointing towards the negative by definition of our positive test charge that everybody would use. So the field points towards the negative but away from positive. So it's pointing away from the positive test charge but towards the negative. Alrighty. The International System unit of electric field. There it is, guys. It's the Newton per Coulomb. That's a C for measurement of coulombs, N for newtons. Remember, this is newtons per kilogram for the gravity, but in the E field, newtons per coulomb. There is another unit we'll use later on, but that's for another time. Right now, newtons per coulomb is fabulous. Just like my hair. Fabulous. Alrighty, single point charges. Density of field lines indicate the strength of the field. There you go. So we have, how many of the, is this four lines around there pointing towards the negative, okay? So what if we have only, not four, that's 8, 4 per side, okay? What if you only had 4 total lines instead of 8? Well, that would be half the charge. What if you had 16 total lines as opposed to the 8? Well, that'd be twice the charge, okay? So you can determine what that charge means in terms of lines, but that's one way to describe the amount of charge here compared to something else. This has the same magnitude of charge, but just the opposite. The lines go away, because here we have 8 lines as well, okay, for the single point charge. If I have 2 positive point charges there, I would have not 8, but 16 all going away. We'll look at that in a little bit, and you're going to look at that in a lab yourself. I'm going to actually let you save that for doing on your own thing when we do a lab and look at fields and everything. So definition of electric field for a single point charge. There it is, guys. Oh, so remember, force is the KQQ over R squared. But this is the test charge, which is one of those Q's. So, pew, the charges go away. And that means what you have left over is the test charge is gone. This is the test charge. The test charge is gone. The little charge near the field is gone. This is what makes the field, the big charge. So this is another way to find the electric field. Okay? Always points in the direction of the negative and away from the positive. Okay? So I guess we have time to do this. We'll do this real quick. We'll run over the FET right over there in Boulder, Colorado. It doesn't take too long. Checking the time, checking the time. Alrighty, guys, so there's nothing much going on there. Hey, there's one charge. Look at that field going all away from that thing. Okay? By the way, these things don't move anywhere. So these are just little things that show the electric field lines up. So if I have another positive in there, boo! Oh, now we're repelling. Look at that, guys. Now we're repelling. It's a field fight. Okay? They'd actually kind of bend away from each other. It's easier to see if I move them down like this. Field fight, they're kind of pushing away. And they get weaker as they go away. As you notice, it's getting a little dim there. What if instead I have a negative in, 2 positives? Well, you can't see there's twice as many lines the way this is set up, so that part doesn't work very well, I guess. But if I put a negative in there, bam, oh, look at that. Now they're attracting, but they're pointing towards the negative away from the positive. What if I get 2 negatives on there, guys? Ooh, look at that. It's getting even stronger and stronger and stronger. You kind of get the point. Okay? Alrighty. So, let's go back to our, not that, this. And now, this. Okay, there's your electric field. There's your distance squared. Still the inverse square law. Get twice as far away, 1/4. Get 3 times further away, it's 1/9, and so on. That's your charge that makes the field, and that's your constant. That's your 9 times 10 to the 9th thing. Newton meter squared per coulomb. All right. Oh, so here we go. So that's just more the same thing, pretty much. So you got one charge, they point from one and they go into the other. So if we have as many leaving as coming in over here, they're the same magnitude of charge, this opposites. Okay. And there's some other example of a picture doing the same thing. And there's a repelling, these are attracting, these are repelling each other. And repelling, and who knows what they actually used. If they actually using a magnet there, more than likely, and iron filings, I think is what they're doing. I think they're lying. Oh, there it is. Opposite magnetic poles, okay, and alike magnetic poles. These are electric fields, not magnetic fields. But yes, they do look the same. They do look the same, even though magnetic field lines are not the same thing as electric field lines. More on that another time. All right, example 1. Here's for the mathletes in town. Okay, how do you find the electric field at 2 meters away? Notice there's nothing there. Because if you had a known charge there, you'd talk about the force between the two, whether it's repulsive or attractive. We just want to know the field at 2 meters away right over there. Okay, so the strength of the field is, it's just you plug it in. It's a milli thing. That's a lot of charge, guys. A lot of charge. Per that, and it's a good size field, guys. Look at that. It's 11.3 million newtons per coulomb, which is 1.13 times 10 to the 7th to the right. Because so this is positive, guys, because there's no negative on there. It's positive. That means the field's to the right. Okay, let's see if example 2 is any better. All right. So find the force on a proton placed. Oh! So now if you put a proton into there, you could do that formula you did already for the force stuff, but since you already have the field, what's the point? Since you already have the field, solve for the F. It's the field times the test charge you put into there, and that test charge being the proton. And the proton is the fundamental unit of charge, the smallest you have there, 1.6 times 10 to the negative 19th times your field, bam! And since it's a proton, it's repulsive. That's why it's to the right. And doesn't seem like a tremendous force, guys. That's a teeny mass. And at some point, you may have to find the acceleration of that, because it's doesn't seem like a very big force. It's a really small mass. It's going to seem like a tremendous acceleration on that thing. Or, oh, yeah, that big thing. But since you already did the field, you don't do it again. If you hadn't done the field to begin with, you just would have done this and got the same answer. That is correct. Alrighty, guys. So that's the end, because this stuff is going to be after the holiday, all about potential energy and potential. The good news is there's scalar amounts. And you might say, why is it good news? There's no angly things. 5 plus 7 in scalarton, always 12. There's another answer. 5 plus 7 in Vectorville with your fields or forces, it can be as much as 12 or as small as 2. So the math is a little more complicated with vectors. Not so much with this scalar stuff. So it's actually a little easier to work with. Okay, and it's pretty handy stuff. We don't have time before the holiday. This is after holiday stuff. Happy holidays, everybody.